Hello everyone and welcome back in our class of Foundation Engineering. We are going to continue the chapter number 2, the in-situ soil testing. Okay, last time I believe we did the standard penetration test, SPT testing, and this video will be about cone penetration test. Okay, so we are going to make two videos on this part of this chapter. Okay, this first one will be just about the test, the equipment that are used in the test, and how the test is done. Okay, and in the next video we will deal with the data, how to interpret CPT data, and how to obtain soil parameters from CPT result. Okay, we can obtain all, actually many soil parameters from CPT test, more than the SPT test. Okay, so but that will be the next video. Okay, as you can see, this is the part 1. So okay, let's go. The cone penetration test introduction. So this the cone penetration test is a test where a cone on the end of series of road, okay, the drilling road, at the end of the many road, there is a cone, okay, and that cone is being pushed in the ground, okay, at a constant rate. The penetration rate of the cone is constant, and it is continuous. We can do continuous measurement, okay. The continuous measurement of the resistance to the penetration can be obtained, and also the surface leaves, the cone resistance and surface leaves, okay. So this figure is showing us a lot of, giving us a lot of information, okay. So we can see here that there are several types of cone. This is the cone. As you can see, the shape is like a cone. This is being pushed in the ground, and here is, this part is the cone, okay. So there is road here, one road. So as you may guess, once we push at the end of this road, we have to add a new one, okay, to push it continuously in the ground. So we can see some terminology here, okay. This is the code, actually, only this part. You can see it here in photo with different sizes. And we can obtain here the pour water pressure is obtained here from, this is the filter of pour water pressure, okay. And the friction sleeve is this part, as you can see, this part, okay. So the whole thing now is penetrometer, okay. So doing cone penetration test is pushing this cone into the ground, that's all. So we have CPT, which is cone penetration test, and we have CPTU, which is this case. CPTU is when the cone penetration test is allowing us to get also pour water pressure. We measure both. In that case, we talk about Piezocone test, okay. This is now the one that is mostly used, okay. This ring, you can see here, this part is the part that is giving us the water pressure, the pour water pressure, okay. Let's say pour pressure, okay. So CPT and CPTU, please, you should know the difference between these two, okay. This one is not giving us pore water pressure, but this one gives us the pore water pressure. Okay, so sorry. So the total, because we are pushing, you see these forces are pushing the cone into the ground, okay? The cone being pushed, you can guess that there will be a resistance against that force, right? So the total force acting on the cone, okay, let's say this force, the force acting on the cone, let's call it QC with capital Q. Okay, the capital Q just means it is in like kilonewton or newton, okay? Not in pressure, in terms of force with capital C, capital Q, the QC. And if we take this QC, we divide it by the area of the cone, okay? Projected area of the cone. See this here, there are different areas, right? So we project the area, okay? And we can get AC. AC is the projected area of the cone. So force divided by area gives us pressure, right? So if we do that, we can obtain the cone resistance, QC. You can see this one is small q, okay? So this one is in like pressure unit, like kilopascal or pascal, kPa, mostly kilopascal, and here is kilonewton. So the force divided by the cone area, we got the QC, okay? Here is an illustration of what I just said. The cone is here, right? So the force coming on the cone divided by the projected area of the cone gives us this cone, the pressure, the cone resistance, okay? We are just here, okay? And then if you go now for the friction, the sleeve, okay, this part of the cone, okay, this part, the sleeve friction, okay, the force, these forces acting on the sleeve of the cone, or let's say of this penetrometer, okay, if we divide that force Fs, we divide it by the surface area of the friction sleeve, all this surface, okay, the surface, the body surface of the penetrometer, this part, okay, it will give us the sleeve resistance, Fs. Is a capital F, this one is the small s, F, né? Okay, so sleeve friction. And of course, the last one is this part gives us the pore pressure, okay? So in piezocone only, piezocone, I have defined I gave you the definition of the piezocone previously in the previous slide, right? So piezocone, the pore pressure is also measured typically behind the cone U2, okay? U2. U is just for the pore water pressure, okay? So in this video, we are just going to talk about detail about how the test will work, how to perform the test and everything. And in the next video, we will try to see how the test result, how is the test result and how to interpret this test result. Okay. Next, we are going to talk about the test equipment and the how we perform the test. Okay. How we do the test itself. The test equipment first. First, cone penetrometers. The cone penetrometers, we have many. They are here. We have already shown this in the first slide, I think. These are the penetrometers, okay? So these penetrometers come with range of sizes, okay? We have 10 and 15 square centimeter are the most common sizes. These are these two actually. This is 10, this is 15. These are the two common sizes that are used. Okay. These are the most standard sizes used. And this photo is showing us 2 square centimeter. This is the section. Okay. The diameter of the cone. The diameter of the cone. 2 square centimeter, 10 square centimeter, 15 square centimeter, and 40 square centimeter. Okay. So these two in the middle are the most common. Maybe these are mainly used in like a small scale test in a lab, for example. You can use this small one. Okay. A Mini-CPT. So I already explained this. So this mini cone, this one, okay, these are used for shallow depths, shallow investigation. Okay. But the large ones, these large ones, are used in like gravel, because when the soil is hard, as you may guess, the penetration also will be like difficult. So we use this big one, okay, the large one, for gravel, so gravelly soil. Okay, this is penetrometers. Okay, so for these penetrometers, we have generally two types. Okay, mechanical friction cone penetrometer. This is shown here, just some detail. You can see this shape is when the cone is collapsed. This one is when it is extended. You can see here, this portion here is 69 millimeter, and here is 33.5 millimeters. Okay, so this mechanical cone, the tip of this penetrometer is connected to inner set of rod inside, inner set of rod inside. And the tip is first advanced for 40 millimeter, giving the cone resistance. Okay. And then after that, we do like pushing the cone, and the tip engages the friction sleeves. Okay. And the inner rod advances, the rod force is equal to the sum of the friction force and the cone. Okay, the vertical force is like for the cone and the sleeve, the sum of these two. Okay, the total force. Okay, then if you subtract the force on the cone, you can obtain the side friction resistance. Okay, the other one is electric friction cone. This is the one I prefer actually. So for this one, the tip of the penetrometer is attached to a like a string of steel rod. Okay, this is example. The rod are not here actually, and from number 1 to number 8, okay, 7 is here. You can try to know the names. Okay, number 1, this point. Number 2, load cell. This load cell. Okay, this part. Number 3, strain gauge. This is strain gauge. Okay. Number 4, friction sleeves. This number 4. And number 5, attachment ring. This one. Number 6, waterproof bossing. The bossing, waterproof bossing. And number 7, cable. This cable is connected to the PC that is recording the data. Okay. Number 8 is connecting rod, the connection rod. So you put the rod in here. Okay. And so on. So here is an example. you can see here a photo of this type of penetrometer, and you can see the cable. So the tip of this penetrometer is pushed in the ground, okay? And the push is pushed in the ground at the rate of 20 millimeter per second, or you can say like 2 centimeter per second, okay? 2 centimeter per second. So the wires from the transducer are fed through the center. You can see the center of, as you can see this one also, the cables from the center of the road, from this kind of road, okay? And continuous measure the cone and side resistance, okay? With this connection, we can continuously measure both the cone resistance and sleeve resistance, okay? Okay, so for this part of equipment, we have additional sensors or modules. Sensors or modules, okay? So since the introduction of this electric cone, the one I just presented now, okay, in the early 1960s, many additional sensors have been added to the cone, okay? So we can measure temperature. The cone, we can put a temperature sensor in this electric cone. So it gives us the temperature as the the test is going on, okay? Geophone, do you remember geophone in the geophysics testing? Geophysics testing. Geophone for seismic wave velocity measurement. Okay, we can include it, put it in also the cone, and we can measure the velocity, seismic velocity at the very deep part of the ground. Okay, pressure meter also. Okay, cone pressure meter. We can get that. Camera. Okay, visible light. Radio isotope, gamma or neta. This is maybe not all of them are for geotechnical engineering, okay? Electrical resistivity and conductivity. That one also, we, in the geophysical testing, we talked about this one last time also, okay? Dialectic, pH, the pH of the soil. Sometimes we can use CPT to measure that one also, okay? Oxygen exchange, redox. This is, not all of them are for geotechnical engineering, okay? Laser also, ultraviolet induced fluorescence, and also membrane interface probe. Here is example of the seismic CPT, just an illustration, seismic CPT, okay? So this cone, they are putting like sensor, seismic sensor, to measure the wave velocity of the soil, okay? So you can just check. And here, you can see here, hammer with contact trigger, okay? The trigger circuit is here. And you can see here the oscilloscope that is showing and this screen is showing us the result, the CPT data, okay? Cone data obtained, right? So because in this video, we have decided to not show the CPT result, how is CPT result is presented in this. But in the next video, we will see that it will be just graphs like this. Okay. So next we are going to talk about pushing equipment. Okay, because CPT, as the introduction says, it's just about pushing a cone in the ground. So what are the equipment used to push the cone in the ground? Okay, there are different type of equipment. Okay, so pushing equipment consists of push like rod, a drilling rod are push, and those rod push the cone into the ground. Okay, so to thrust the mechanism and a reaction frame, because you need reaction frame to push it, okay, on the land. So on the land, because we can do CPT also over water, okay. So we are going to see on the land how does this works. Does it work? So pushing equipment for land apply generally a application generally consists of specially built unit. There are units built for just the test. Okay. Sometimes they are just like trucks or truck mounted. So the CPTs can also be carried out using the this kind of drills, anchored drill rig. An example is here. You can see this truck, for example, is specially made for this CPT. And inside the truck, you can see this. You move just this, and the hole is here. Okay, and the cone is passing through the hole, and you can see out here. This is under the truck. This is under the truck. Okay, and the cone is coming out and being pushed through here, through this hole inside. Okay, and as it is said here, we need like a reaction frame. So here, for example, is like 25 ton CPT unit. It's heavy, so we can push the cone. This is just example. Okay, there are many type mechanisms, and also we have this kind of unit. Okay, this one is a 20 tons, 20 tons CPT unit for this one, and this one is a small anchored rig unit. This one, there are many model, many types, and this one is a portable one. Okay, for CPT, for example, inside a building, you can see it's very compact, very small. So you can do it in the basement, for example, or any place that you don't have enough space, okay, inside the building, for example, or limited access. Okay, another mini CPT system that is attached to a small truck with auger rig. Okay, you can see auger rig. Okay, there are many types. So there are some technicians who are specialized in this performing the test. Okay, we can do also CPT over water. Okay, we can do CPT over water. So these are like there is also a variety of pushing equipment for over water investigation, depending on the depth of water. Because sometimes if you are doing this on sea, okay, we have this kind of like floating or jacked up this kind of equipment for shallow water depths around the if the depth is less than 30 meters, we can use this kind of equipment. Okay, and this is, for example, jack up boats. This one. Okay, this kind of ship is floating right on the water, right? Yeah. So this kind of uh, system is for when it is not too deep. Okay, 30 meter maximum depths, we can use this kind of system. But when we go deeper, in deeper water, for example, higher than 100-meter deep, in that case, we have to use more specialized. We have to use specialized equipment. Okay, the pushing equipment. Okay, on this, there are this kind of equipment. We put this down, okay, on the seafloor, okay, using specialized, especially designed for underwater system. This kind of system, you just put it down until it reach the seafloor, and then you can perform your CPT. Okay. And if we reach the seabed system, this kind of system can push full size cone. We have seen different sizes of this cone, right? Of cone, from two square centimeter to 40, right? And we have agreed that 10 and 15 square centimeter are the most common. Okay, so this system can use these 10 to 15 square centimeter cones. Okay, so alternatively, it is also possible to push CPT the CPT from the bottom of hole using downhole equipment. Okay, if you know downhole equipment, this kind of equipment are used mainly in oil mining underground. You can see this one is water at the bottom of sea, and it pushing this kind of equipment. But for CPT, it doesn't work exactly like that. This is just the definition to let you know what is downhole equipment. Okay, so the advantage of using this kind of equipment is that it can allow us to perform the CPT drilling like much deeper penetration. We can obtain much deeper penetration using this kind of system. Okay, and also hard layers can be drilled through if we use this kind of uh, downhole equipment. Okay, the downhole equipment method can be applied both onshore or offshore. Okay, here is an example. Okay, you can see this is downhole cone penetration test. This is equipment used. You can see this, it can go very deep. Okay, downhole equipment for CPT, and you can see the screen here, and it just remotely controlled. Okay, here is an example for downhole seismic CPT. That one is seismic. Okay, you can see this equipment is the one here. Okay, and we use this pulley to put the cone down deep in the water seabed. Okay, so recently also there is like a remotely controlled seabed drilling rigs that can drill and sample and push CPT in up to 4,000 meters, very deep. Okay, this is example. This is just like a sound, a portable remotely operated one. The name is here, portable remotely operated drill. Okay, P like prod. This is just for your information. So 4,000 meters, it is not small actually, very deep. Okay, let's go now to talk about the depths of the penetration. Okay, CPT can be performed to depths exceeding 100 meter if the soil is soft, okay? And if we have large capacity pushing equipment. We have just talked about the type of pushing equipment, and they have different capacities. So to improve these depths, the penetration, okay, we can try to cut the friction along the roads, pitching roads, okay? Pitching roads can, the friction along the I'm not talking about the cone, penetrometer itself, the road that you are adding road, making the road long. So the friction along these roads are sometimes very high. So if we can cut this friction, okay, if we can reduce them, we can improve the penetration. Okay, so this can be done also using expanded coupling to friction reducer to reduce the friction. That is just about 1 meter behind the cone. Okay, and the penetration will be limited if a very hard soil like gravel layer or rock are in the ground. Okay, so it is very common to use 15 square centimeter cone to increase the penetration depth. Okay, because this is robust. This cone is very robust and has a slightly large diameter than the one of 10 square centimeter pushing rod. Okay, so to push the pushing rod also can also be lubricated. Okay, because if you lubricate, it will cut the friction. Okay, it will remove the rod friction and allow you to go deeper. Okay, deep sounding. So depth of penetration can also be increased using downhole techniques. We have just explained that downhole techniques can allow you to go very deep. Okay, this is what we can say about the depth of penetration. Okay, now how the test is performed. How do we perform the test itself? So the pre-drilling, sometime in some condition, pre-drilling for penetration in field or hard soil, it may be necessary to make this pre-drilling in order to avoid damaging the cone. You will not go and just start using the cone. Maybe sometimes the surface layer is very hard. So just remove that layer before starting using the cone. Otherwise, you will just damage the cone. Okay. This pre-drilling is in certain case may also be replaced by first pre-punching. You just punch the surface, okay, and make a hole through the upper problem material. The upper layer, maybe it's just gravel or rock. You can break it and make it easy for the cone to start to be pushed in. Okay, so it can be done with a solid steel dummy prop with a diameter slightly larger than the one of the cone. Okay, it is also common to hand auger first, like using the hand, the augers to up to 1.5 meter in urban area. This is to avoid the underground utilities. Okay. Verticality. So when you are performing the test, you have to check if the equipment rod, the cone is vertical. Okay. So when you are pushing, the pushing machine should be set up to should be set up so that the pushing direction is like vertical. The way you are pushing the cone, it should be vertical. So you should set the machine, the pushing equipment, vertical, so that the pushing direction is vertical direction. Okay. So the deviation of the initial pushing direction from the vertical should not exceed 2 degrees. 2 degrees maximum. It should not decrease 2 degrees. Okay. So we should check the straightness of the rod, the pushing rod, to confirm that the 2 degree is not exceeded. Okay. More modern cones, we have modern cones that have simple slope sensors that gives us the inclination at any time. In the cone, we can put inclination sensors to obtain the inclination and check if it is out of 2 degrees or not out of 2 degrees. Okay. So it allows us to measure the non-verticality of the sounding. Okay. This is useful to avoid damage of equipment and breaking of the rod, the pushing rod. Okay. For depths like less than 15 meter, significant non-verticality is unusual. So it is like shallow, can be considered that it is shallow. That provided that the initial pushing direction is vertical. If the initial pushing direction is not even vertical, so it will be difficult to, like not difficult, impossible to avoid non-verticality. Okay, so just remember that the test should be performed in the way that the cone is vertical, and the verticality, the inclination should not exceed 2 degrees. Okay. Reference measurement. Okay. Reference measurement is just to make sure that there is nothing that is affecting your test. Okay. For modern cones have a potential for high degree of accuracy and repeatability. Okay. So if you are using a modern cone, maybe you don't have to worry too much about errors. Okay. The accuracy is high. So the test has shown that output of sensor at zero loading. It means you test all the sensor, temperature, inclinometer, all of them. Okay. You test them at zero loading. That means no pushing yet. And you check the value. Okay. Because the sensor at zero loading can be sensitive to change in temperature. Although the most cone now include some temperature compensation. They compensate the temperature effect. Okay. So it is common to record the zero loading readings. If you read zero loading inclinometer inclination, how to say, temperature, you measure the friction, cone resistance, pour water pressure, everything that you will measure during the test, measure it at zero loading and check. Okay. all sensors, and you track these value, you track any change in this value. Okay, so zero loading readings should be monitored and recorded at the start and at the end of each CPT. So after the end of the test, you do zero loading reading again to check if there is any change. Next, rate of penetration. I think I have talked about this at the beginning also. For the electrical cone, the penetration, standard rate of penetration is 2 centimeter per second. Okay, approximately 1 inch per second. Okay, so according to that, then we can do sounding about 20 meter for about 30 minutes. Okay, about that. So CPT results are generally not sensitive to slight variation in the rate of penetration. If the rate of penetration is like changing, but not too much, then we can still consider that the data, the result is not affected. Interval of reading. So the data, at what interval are you sampling the data? Okay. So electric cone, for example, allow us to obtain continuous data, continuous analog data. Okay. However, most systems convert the data to digital form, okay, so that you can read. And for that, you need a selected interval. Okay. So most standards require the interval to be no more than 200 millimeters. Okay. In general, most systems collect data at interval between 10 and 50 millimeters. 20 millimeter is the more common interval. So every 20 millimeter, you take data. Dissipation test. What is dissipation test? This is about the excess pore pressure. Okay. During a pause in penetration, okay, any excess pore pressure generated around the cone will start to dissipate. Okay, so the rate of dissipation depends on several factors. It will depend on the coefficient of consolidation of the soil, which in turn depend on compressibility and permeability of the soil, as we know. Okay, so the rate of dissipation also depend on the diameter of the probe, the cone. Okay, so dissipation test can be performed at any required depth. At any depth, you can perform dissipation test by stopping the penetration. You just stop it and measure the decay of pore pressure with time. Okay, and sometimes it common to record the time to reach 50% dissipation, which is T50. Okay, here is an example. This one is when the time is here in log time. Okay, log scale. Here is square root of time. So this one is better for short dissipation. Is less than 100%. So T50 here, okay, you can see it's around 85 seconds. T50 here, 85 seconds. T50 is half, 50% of dissipation is reached. So for this test, you just stop the penetration and measure this dissipation. Okay. So if the equilibrium pore pressure is required, the dissipation test should continue until no further dissipation is observed. Okay. This can occur rapidly in sand, but as you know, in clay, plastic clay, the water is not dissipating faster than in sun. In clay, then it will take it may take hours, several hours. The dissipation rate increases as the prop size decreases. Calibration and maintenance. So calibration, if you are using this equipment, any equipment you are using, you need to maintain them. Okay. The calibration should be carried out at interval based on stability of zero load reading. Zero load reading, we have explained this. This is just readings when you are not pushing. That's no pushing at the beginning or at the end. Okay. For many projects, the typically, if the zero load readings remain stable, the load cell do not require a check calibration. Okay. Like for many projects now, check calibration can be carried out before and after the field work with functional check during the works. Functional checks also should be checked. Functional checks should include recording and evaluating the zero load measurement. Here is like a table that is giving some kind of summary of checks and calibration for the cone CPT. Okay, the wears, okay, O-rings. I will show something here. This is our cone, our penetrometer. Okay, so if we disintegrate the cone, the penetrometer, we will get this kind of equipment. These are the parts of the penetrometer. Okay, so you can see the cone is just here. You can remove it actually and store it somewhere safe. Okay, and we have a lot. This one is a filter, a ring filter, and we have a lot of O-rings, this kind of rings. So these O-rings seals, this O-ring friction sleeve, O-ring probe, O-ring, not this one here, O-ring, another O-ring is here again. This one also. This one is a CPT X-ring. Okay. Another O-ring for CPT point. So there are many of them. So at the start of the project, okay, at the end of the day, we need to check. Okay. In the road, pushing road, I think at the beginning, I saw what is pushing road. You need to check them at the start of the check of the test, because if the pushing rod are damaged or like are not straight, then it will affect your test. And also once a month, you have to check them once a month. If you are using it permanently, please check it once in a month. Okay. The power pressure filter, there is a filter here, this one, the power pressure filter. Check it at the beginning of your project and at the start of the test. Okay. And calibration also. Calibration, remember that calibration is normally carried out only when the zero loading. We explain what is zero loading here. Zero loading readings. If these zero loading readings are affected, you see that the zero loading readings are not really good, then you can check, you can do calibration. Okay. And the PC computer also, you are using computer to record this kind of thing. Okay. You can see here this PC. This is just an illustration. So the cone is here and you record, you need the PC. You can check it also Yeah, once in a month. Okay, the cone itself also once in a month. This cone, this is the cone. Okay, zero load. So this zero load at the beginning and at the end of every test, beginning and end, to perform the zero loading to check if the value are correct, are not out of like normal values. Okay, and the cable, as you can see, the cone here, we have a lot of cable. Please check this cable at the start of your project, and once in a month, please check the cables. If you're frequently doing the CPT, check the cable if they are not damaged. Okay, so this is what is allowing us to record the data. Okay, I think that's all for this. Next time we are going to talk about the CPT result. CPT result means we have to interpret the CPT result and know we have to check how to obtain the soil parameters from CPT result, CPT data. Okay, so that will be all. Thank you very much for your time and see you next time.